We now consider another example of the velocity transformation problems. In this case, we've got Nolan Ryan on a rocket. Again, Nolan will be our primed observer, and our batter here will be our unprimed observer. Let's give him a little home plate here to guard. He's not going to have prayer hitting it, but we'll let him do that. Nolan throws again a 100-mile-an-hour fastball in the X direction. That's the velocity of the baseball seen by Ryan, the primed. Ryan is seen by the batter, which is capital V, going up at 50 miles per hour J hat. Okay, so the first question says, what is the velocity of the baseball? I remind you of our velocity transformation, that the velocity of the baseball equals the velocity of the baseball seen by Ryan plus the velocity of Ryan as seen by the batter. And we have all this information above. All we have to do is put it in and apply vector mathematics. So here's an example where you can't just do your intuition and add the two speeds together. You actually really have to know the vector nature of velocity. Again, we know that this was 100 miles per hour in the X direction as seen by Ryan, and he saw the baseball going at 0 miles per hour in the Y direction. Ryan's velocity as seen by the batter was 0 miles per hour in the X direction and 50 miles per hour in the Y direction. Add the two vectors. You have 100 miles per hour in the X plus 0 miles per hour in the X. That gives you 100 miles per hour in the X direction. You add 0 miles per hour in the Y, added to 50 miles per hour in the Y. That gives you a total of 50 miles per hour in the Y direction. And that's the final velocity vector as seen by the batter. He sees a baseball coming toward him, but also rising. And this is interesting because actually a baseball in a normal game of baseball cannot rise. It doesn't spin fast enough to create enough of an upward lift from the air force to offset gravitational force. Unlike a softball, which because of its larger size and windy can. In order to make a baseball do it, you'd have to spend something in the order of really thousands of RPM, and nobody can do this. We'll cover that when we cover fluids later in the semester if we have some time. Let's go ahead and look at another thing that could be asked. Sometimes people, instead of asking part A, they just ask you this part B, which is what is the speed of the ball as seen by the batter. And in this case, what they're really doing is they're asking you to find the velocity, and then when you're done with the velocity, to find the hypotenuse, that is the magnitude of the velocity. So we have, from our previous work, 100 miles per hour on this side of the triangle, 50 miles per hour on that side of the triangle. And what we're now being asked for is to find the hypotenuse. That's the speed. So we just need the Pythagorean theorem, since we've done all of the work on the component parts. And taking square root of the x component, which is 100 miles per hour squared, and squaring the y component, which is 50 miles per hour squared, and we get approximately 112 miles per hour. Should check your work. We knew that the hypotenuse had to be bigger on either side, so we knew this was the biggest other side, so it had to be greater than that. So this v had to be greater than 100 miles per hour. And we also knew that it had to be less than the sum, since it's a triangle, so it had to be less than 150. So more than 100, less than 150. This side is quite a bit much bigger than this, so it should be closer to this than it is to 150. So sure enough, about 112. Makes sense. All right, let's look at one last thing, and this is an important concept. You can never measure absolute motion. Motion is always measured with respect to an axis. There is no special axis. Put another way, it is meaningless to say an object is at rest. You can say it's at rest with respect to the earth. It is at rest with respect to the moon. It is at rest with respect to this classroom. But there is no such thing as absolute motion, so there's no such thing as absolute rest. All right? Rest is just a special case where the velocity is equal to zero in a particular reference frame. In another reference frame, it may not be seen at rest. So for instance, you're in a car, and in your reference frame, if you have a book on your lap, it's at rest with respect to you. It is not at rest with respect to a person outside the car when the car goes by them at 60 miles an hour. So this was a very important concept. They spent a lot of time on it. It still gives students a lot of trouble, but I emphasize that you should think long and hard about this. Motion is measured relative to an axis. You cannot measure absolute motion, only relative motion. The study of these equations are called the Galilean relativity, and they are the Galilean transformation equations. The relativity meaning relative velocity, relative motion, and it was developed by a guy by the name of Galileo Galilei. He not only knew the equations, but he understood why they were true. It was the study of this motion in electromagnetism and the fact that there were problems between these two fields that led Albert Einstein to determine that these equations were not valid at high speeds. And he went back, and there was another person who had developed some equations with a different view called Heinrich Lorentz, and the equations are named the Lorentz equation. Einstein re-derived those equations from a new point of view, a new way of looking at space and time, in what is called the special theory of relativity. Those equations lead to unique ideas that classical physics wouldn't allow, such as atomic bombs, nuclear reactors at Comanche Peak, if you would, lasers, computers, your modern electronics. The largest semiconductor producing group in the world is the Dallas-Fort Worth Metroplex. The third, it happens to be the Austin area, the so-called Silicon Hills. Einstein's work has tremendous impact on the economy of the state of Texas. All right, and depending on how much time, we'll come back and look at that maybe, or you'll study it when you get to modern physics. Finally, when we say relative, people say, oh, any answer is relative. You hear this with sociologists, psychologists like to say that. That's not what Einstein was saying. It's not what Galileo was saying. It is the observer who is relative, not the answer for the measurement. In each frame, there is one answer to the problem. So you can't just put any answer you want down and think that I have to count it right. I don't. But you can put the same answer as the person next to you, and if you're in different frames, just because your answer might be right, the other person's answer may not be right if they're in a different frame. The answer that is correct is dependent on the frame. So what is relative is the observer. There's no special observer. It does not say that you can just put down any number for measurement. When you make a measurement, you would get one answer. All right? If I know the measurements made by one person in their frame, and I know another observer's frame of reference, I can predict what their experiment will show me, whether they be on a rocket or whether they be on planet Earth. This finishes this section, and we'll go on now to acceleration.